Okay, looks like the recording's going. No one here joining me at 7 o'clock tonight for the review session. So I'll just do a couple of quick problems, maybe a couple notes on what might be helpful in their study. I'll post this to YouTube in a little bit, and maybe some people use it, maybe not. All right, so let me share my screen, and we'll get on with it. Okay, so should kind of see the writing pad right now. I guess the first thing to say about the test is going to be 3 questions. Hey, we got somebody in. Look at that, it's Andrew. So I'm just going to kind of go over some quick review things unless you have specific questions. 5-10 minutes maybe about maybe what to expect on the exam, good things to do to study. Then we can look at some practice problems. So first things first, I was thinking about a good way to review, and honestly, I think the best way to review for the test is to look at these combined loading notes, which you can find on Canvas. So this portion of the test, we're going to have questions about torsion, questions about bending, question about transverse shear. Axial loading was kind of in test number 1. And then all of those things together. So I think this set of notes, if you just want to review for yourself what each of those different types of stresses is and where they come from and what the equations look like, can be pretty helpful. So take a look at these guys. You know, the equation should be pretty comfortable at this point. Sigma x, px over ax. Bending, we've seen it's this linear equation. Looks like my over I. Negative sign pops in there because when you have positive values of y, you're going to be in tension in this particular orientation. Transverse loading looks like Vy QZ over IZT when you just have one load kind of coming across the face. It's one load across the face, giving sort of a distribution of shear. It's greatest in the middle and 0 at the top and bottom. We have this kind of weird term called the first moment of area. Q is Y bar prime A prime. And this is a nice little example showing what that actually looks like. So let's say your point of interest here is right across or somewhere that lies in this plane defined by this variable t. We want to define the area above that line, which is A prime, and then the centroid of that area A prime is located some distance above the neutral axis. That's what this NA stands for. And so A bar prime times Y bar prime is your first area moment of inertia, which we label Q. Lastly, your torque given by TR on J. This is again a linear relationship where R is the radial coordinate from the center, so 0 at the center, and then the shear stress increases linearly on your way up to the edge of the bar. We can put all that together when it comes to combined loading, so the rest of the notes kind of explain that idea by sort of picking up those forces wherever they may be. Let's say you're interested in this particular member here. You're interested in points H or K. Here's sort of some random points on the bar. Well, what you'd want to do is you want to cut half of this at that cross-section and relocate everything to that cross-section, moments, forces, torques, etc. And then use those pieces of information to derive the stresses that must be present inside of that cross-section for that equilibrium condition to exist. So I think that's probably the best way to study this portion of the exam is to just look at combined loading and do a lot of combined loading problems. Now, the practice problems that I laid out for you, which I'll just throw in here really quick, they kind of go one by one down the row. So we have torsion, a couple questions on torsion. You have bending, a couple questions on bending, transverse shear, and then at the very end, the combined loading. The combined loading questions in this practice set are, I think, particularly difficult. So if you can make your way through the combined loading questions and understand those well, I think you're going to be perfectly fine on your way, especially this last one. This last one basically has every possible stress component that could come into play. So if you can do number 10, you're going to be well on your way. So we have 2 gentlemen here. I was going to maybe do one example from each of these particular sections, just running it down really quick. Are there any questions in particular that either of you would like to see before I just kind of dive in and start doing a few?
Not necessarily a question, but I remember I asked you the other day, like with Q, how you would know when it's 0 or not. Could you go over that one more time?
Sure. Okay, so Andrew wants to know about this variable Q, which pops up from transverse shear. So let's maybe look at an example that's kind of simplistic. All right, so here we go with an example. All right, let's just say that we have some bar fixed into the wall. Maybe something that looks like this. Forgive the picture. Kind of coming up with this on the fly. But hopefully you can sort of understand what I'm doing here. And let's say we have like two loads that are kind of coming across the face. Something that looks like this, something that looks like this. And let's put a coordinate system on here, kind of a typical coordinate system that we're used to. X down the bar, Y up, Z to the left. All right. So let's now say that we have, a cross section here that we're interested in looking at. And we've got a couple points of interest, maybe one on the top and one on the left. Let's call the piece on the top point A and the part on the left point B. And let's just say, for numbers' sake, that this is 10, this is 20, and this length here between them, let's say this length is 5. Who knows? Okay, 5 inches. And let's put units here, pounds. Okay, so if you're going to attack this with like a combined loading type methodology, you're going to relocate forces and moments. So forces relocating, you'd have negative 20 j hat minus 10 k hat. And then for moments, you'd have something like 5 I hat crossed with that force, negative 20 j minus 10 k. Okay, and we can go through this if you want. I cross j, that would generally give me positive k, but we have a negative sign in front, so negative 100 k hat. And then we have I cross k, would generally give me a negative j. We have a negative sign in front, so plus 50 j hat. This is what you would typically get if you looked at something like this. Great, wonderful. So let's look at what the cross section would look like then with those components added. So here we're looking down the x-axis. Up at the top, you've got point A, and on the left, you've got point B. We can put our forces and moments in. We have the negative 20j, the negative 10k, so we'll just put those in. 10 and 20. And then you've got your moments. Since I have these fancy colors, might as well use them. We have negative 100k hat. That's negative 100k hat's going to be this direction. And then our 50j hat, this is going to be straight upwards. Okay, so your question is about Q, but it's nice to go through this exercise anyways. So let's say we want to examine the transverse shear at A and B. Okay. All right. Well, let's remind ourselves what our coordinate system is here. Sort of have Z to the left, Y up, and X out. Okay, let's look at point A. Your equation is going to look like VQ over IT, specifically if you're looking at transverse shear. There's actually no torsion in this problem. So the only shear stress component that we could possibly have in this problem at any point is going to be from transverse shear. All right. So there's kind of two forces that you're going to have to consider what's happening. There's this 10-pound force that's kind of coming across the negative Z direction. And then we have this negative 20 pounds kind of coming down on the face in the negative J direction. And we're investigating point A. All right. And you could think to yourself, all right, there's 10 pounds, there's 20 pounds here. If I thought about what this is going to contribute, we're on the X face. This guy happens to be in the Z direction. This guy is a shear stress that's on the X face. It's going to be in the Y direction somehow. Both of these being negatives, if you kind of want to assign something to it. Okay, so then the question is about the Q. All right, well, whenever we're sort of looking at these individual forces, let's take a look at the 20 pounds. I always am interested in drawing my variable t first, okay? So if I was like analyzing point B, let's just say for right now, and thinking about this 20 pounds coming downwards, well, I draw a line across my piece at the point of interest, let's call it point B, perpendicular to this 20-pound force, all right? And that would help me define what is the A prime for my Q calculation for that 20 pounds. Okay? Now, in the case of the 20 pounds, when it comes to point A, right, I would want to try to do that exact same thing. Where, okay, at A, I want to try to draw a line at point A perpendicular to this force at my point of interest. Well, in that case, my line is basically 0. Okay, I have no width to move across. Okay, so in this particular case, if you're looking at the contribution of the 20 pounds, in this case, your A prime is 0 for the Q calculation. So tau xy is 0. You comfortable with that?
Yeah, the way you said like drawing the horizontal line like perpendicular, that helps a lot.
Perpendicular to the force?
Yeah.
Yeah. So then if you were to analyze the contribution from this 10-pound load, you would want to make a similar sort of motion. So here's the 10 pounds, it's kind of moving left and right. And so I want to draw a line at point A perpendicular to that force. Okay, well, that looks like this. Okay, now that's separating my cross section into sort of these two areas, sort of the highlighted one that I made on the left and then the non-highlighted on the right. And so in this case, with the 10-pound load, there will be some contribution of tau xz because the Q value will not be 0 in this case. Is that clear?
Yeah, that makes sense.
So if you thought about like rotating this guy 90 degrees, we kind of like looked at this in class the other day. Rotate this 90 degrees, put A on the right and B at the top. And in this case, it would be sort of the 10 pounds down, the 20 pounds to the right. And you're analyzing kind of a similar situation. You just kind of sort of rotated it on its head. Right. Where in this case, the 10-pound force, okay, I'm interested in what's going on at A with the 10-pound force, okay, well, that's nothing. But if I'm interested in analyzing the 20 pounds, or sorry, if I'm interested in the 10 pounds perpendicular to that load, here we are separating this guy into the two sections. Clear?
Yeah, I think I got all that now.
Yeah. Okay. I think that comes into play pretty significantly in problem number 10. Problem number 10 is a doozy. Okay. Any other questions or oh, Michael's trying to get into the review session. Hold on, let me send him a link really quick. Any other questions specifically about topics or even maybe if you want me to do practice problems?
I would say if we could do 10, that'd be very nice.
Okay. Maybe that'll be the whole review because that one's really long.
Yeah.
I gotta get Michael in here. Yeah, that basically has everything. I mean, it has bending, it has torsion, it has transverse shear, it has axial stress. It pretty much has everything. So maybe we'll
It's
just go
like
through
the example.
It is the example. I kind of talk about how I try to make those practice problems so that they like get more progressively difficult. That is like the last problem on the set for a reason. All right, so let's just do number 10 and we'll make that sort of the whole review session because there's a lot to talk about with number 10. It'd probably take us half hour, maybe longer. But it has everything, more or less. Okay. I'm just going to copy it down here and bring it in. This bad boy, this mother of all problems. Huzzah! And we're only analyzing point B. Imagine if we had to do A and B. Okay. So really what you want to do here is you want to find stress state at B. Okay, that's what we're analyzing here. And B is sort of here on this particular side of the bar. All right, so we've got three loads that are applied to this bevel gear, the 200 pounds, the 125, and the 75. They're in cardinal directions, right? So that makes it a little bit easier, but we still kind of have a pain in the butt is that we still have all three. And not only that, but our position vector that locates this guy kind of has two components. So we're going to end up with kind of everything here. All right, this is what I like to call the kitchen sink problem. Okay, so let's get on with this. We're going to relocate our forces. This particular cross-section that contains A and B. And to do that, I'll just pick up the forces and put them there. So the forces that we're going to have here is pretty simple. This is 200 in negative K, negative 125 in I hat, and negative 75 in J hat. So we have negative 125 I hat plus 75 J hat. Yeah, sorry, the Y is backwards here. So plus 75 J hat, and then minus 200 K hat. And now I got to think about my moments. And the moments is the position vector from the cross-section AB. Sorry, arriving at that force, let's just say, arriving at F from AB, crossed with that force. And my position vector is here. So this looks to me like 3 I hat, so 3 in this direction, minus 8 J hat. So positive J hat is sort of like pointing backwards. So since we're going this general direction, kind of to the down left, we have a negative 8 here. So here this is going to be, my position vector is 3 I hat minus 8 J hat. This is inches. And I'm crossing that with my force, negative 125 I hat plus 75 J hat minus 200 K hat pound. Okay, there's a cross product here. There's quite a bit to do algebraically, but it's nothing that's that difficult. I'm just going to kind of cut to the chase and put the numbers down here. So 1600 I hat plus 600 J hat, and then minus 775 K hat. And this is inch pound. All right. So these are the guys we really concern ourselves with. Term, 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 term. All right. Let's take a look at our cross section that contains AB. And we got to put these 6 guys in there. So make yourself a sketch with a lot of space. Because we've got to put 6 things in there. Yikes town. Big circle, rar. Okay. And it's on the top of the bar that we have point A, and on the right of the bar we have point B. Okay, so here's B. And we got a little bit of a different sort of setup here. X to the right and Z up and Y into the page. We have X to the right, Z up, and then Y into the page. So usually we're accustomed to staring on the positive face, but now we're actually staring down the negative face, which makes this problem even more fun. Okay, so this is negative Y face. Very exciting. All right, so let's sort of tackle these one at a time. Negative 125 I hat. All right. I'll do my forces in red and my moments in blue. We have positive 75 J hat, so that's actually coming out of the plane at us. Sorry, that's into the page, positive into the page. And then we have negative 200 K hat. So 200 sort of downwards here. Clean this up just a touch. All right, those are our forces. And then we have our moments. Just one second. I'm doing a review session here. My wife just came home. Okay, so our moments, we have 600 I hat, so 1600 here. We have 600 J hat, so this is 600 into the page. This is my torque term. And then I have negative 775 K hat, so that's going to be okay. So that's a lot of stuff, but we can handle it. Start with the normal stress, which in this case is sigma y at point B. All right, we know normal stresses can come from axial loads and bending loads. Sorry. Can come from either of those two things. And so we just want to try to handle this like we've handled all the other ones. All right. So do I have an axial force pressing on the face here? Well, yes, I have everything in this problem. So yeah, obviously. And the axial load that's pressing on my face is this sort of 75 pounds right here. All right. So here we have what would be Fy on AY. And my bending moments. Well, I have two bending moments here. First, the 1600 pounds kind of coming across the face. And then I have the 775 pushing downwards. All right, so let's look at where the tension and compression is going to happen from these bending moments on this particular piece of the cross section. So this 1600 pounds, you can sort of think of it like this. So stick your right hand out in the direction of the double arrow, right? Kind of keep this idea in mind and do my bending. This is going to sort of want to bend this down, putting the top part here in tension and the bottom part here in compression. So what does that mean about this 1600 inch-pounds and what it contributes at point B? Well, contributes nothing at B. Because B is sort of on the neutral axis here for that 1600 inch-pound bending moment. Nothing at B, nothing that we have to worry about. All right.
I have a quick question.
Andrew, go.
If I might be doing this wrong. If I stick my thumb in the direction of the 1600, I would have that the top would be in compression. Or am I doing that wrong?
Yeah, kind of doing that wrong. So think about you've got the circle in front of you. Think about it being fixed into the wall. All right, that circle there. All right.
Right.
Now, if you stick your thumb out in the direction of the 1600 and you sort of roll your hand sort of towards yourself, it's going to want to sort of like pull the front of the bar downwards away from the wall. Does that make sense?
Yes.
Okay, so that would put the top of that bar into tension.
Okay.
Clear?
Yeah.
Yeah, I know, it's always kind of tricky. The bending moment visualization probably the most difficult.
I might have done this wrong the first time, but I said that there was no stress created from that moment because of the z variable, because isn't it like moment in z times, or moment in x times z over moment of inertia?
Yeah, so in class we derived the following. That looked like this with a negative sign in front, right?
Yeah.
This was very specific to the case that we were looking on the positive x face. Okay. You have to be careful when you're sort of like looking on other axes. Okay.
Yeah.
So in our situation, we happen to be looking on what is the negative y face, which makes this particular derivation kind of tricky. But yeah, we're looking on the negative y face here. But all right, let's take this 1600 for instance. All right, we understand there's going to be tension up here and there's going to be compression down here. This 1600 is in the positive x direction, right? So you would have a situation where a positive 1600 moment in x and a positive z distance gives you a positive sigma y. that clear, Andrew?
Yeah.
And
I-
Jaden?
Yeah.
Yeah. So in that derivation here, you would arrive at what looks like mxz over ix, right? But we're looking at the negative face. So, not so simple.
So doesn't what I said wouldn't that still be true though?
Well, there are other situations where it is not true.
Okay, I agree with that.
Yeah. Sometimes the negative pops in, sometimes it doesn't when it
But
comes
in this case, z would also be 0.
Yeah, in this case, the variable z, when we're looking at point B, is going to be 0, because B
Okay.
is sort of on the x-axis, meaning z is 0.
So is it correct to say that if your point of interest is in the same direction as the moment generated, that it's going to be 0?
If your point of interest is on the line of action of the double arrow, you're at the neutral axis for that bending moment.
Okay,
So yeah, the stress caused by that will be 0.
got it.
Same idea if we investigated the 775 relative to point A.
Yeah.
This thing is going to be in tension on this side and compression on this side from that 775, right?
Yep.
So at A, you would have nothing from that
All right, thank you.
775. Yep. But we're investigating point B, so let's get on with it. The 1600 does not contribute anything at B. It's at the neutral axis for that 1600 inch-pounds. All right. But we do want to concern ourselves with the 775. So like I just mentioned, this is going to want to pull this side in tension and this side in compression. So we're going to have something like mzx over ix. How I would write this? Positive value, because we're going to be in tension.
Excuse me, quick question. The
Go,
reason
Ollie.
why the tension and compression are reversed is because we're looking at the negative y face, right?
Well, yeah, I'm kind of just using the right-hand rule to give me the correct orientation of tension and compression. I gotta make sure.
Yeah, when I use the right-hand rule, I think I might have been having the same problem as the other student who mentioned it, where I'm aligning my thumb with the moment and then curling my fingers, and it's giving me the opposite. So I was wondering if that's because we're on the negative y face.
Well, this is so it's accurate as drawn, right? And you can still sort of utilize the right-hand rule to determine which side is in tension and which side's in compression. So let me just think about this picture for a second, right? This 125 pounds kind of wants to take and drag this thing to the left. You understand that?
Mm-hmm.
That's going to put B in tension, and that's the bending moment we're currently investigating. Is that clear?
Yeah.
So that 125 pounds is responsible for this 775. And that is putting this side in tension. Is that clear? So this guy here is causing the bending moment to sort of pull this entire thing sort of in the negative x direction, which would create a tension at B. We clear on that?
Yeah, that makes sense to me. It's more so the right-hand rule that's confusing me.
So a similar idea. Think about this 775. All right. You put your thumb in the down direction of the 775.
Mm-hmm.
And you think about sort of bending that thing from point B across the 775, right? So I think about sort of, how can I sort of sketch this? Yeah, it wants to like pull B across, right?
Yeah, I get what you mean.
With this sort of motion, putting this side in tension, this side in compression, kind of like I mentioned.
Okay.
So when you do your math there, then you want to make sure that this value ends up with a positive value.
Okay.
Clear?
Yeah.
However you slice it, you know that this is going to give you a tension, right?
Yeah.
Okay. Okay. Let's move on with it then. So at point B, got to be careful with this first term. the force here is in the positive y direction. Remember, y is positive backwards, but we're looking on the negative y face, okay? So in this case, we do have a compression. It sort of makes sense, again, if you sort of look at the picture. Like this 75 pounds is what we're investigating, and you can understand that that wants to push this bar into compression generally, right? So we have a positive y direction, but negative y face, right, for this term here, okay? So we're going to end up with a negative value for the stress when it comes to that compression that we have from that 75 pounds. Yeah, this coordinate system really is throwing everything off, but okay. 75 pounds divided by the cross-sectional area. Here, the bar is 1 inch in diameter, so we have pi times 1/2 inch squared. Now, we talked a lot about why this particular term gets you a positive value. So here we're going to have a plus 775 inch pounds times my x coordinate. Again, the x coordinate is just this distance, which is the radial distance. So that's another 1/2 inch. And then my area moment of inertia, we've done enough of these where we know that a circular bar area moment of inertia, pi on 4, radius to the 4th. All right. So at B, you're going to have negative 95 psi from this guy. So not much happening there from the actual compression load that you're putting on, the axial compression. But the bending that we observe here is kind of dominating here. So 7890 psi. So in total, at B, not a ton of contribution from the axial portion, but a pretty significant contribution from the bending. You're going to have here about 7.8 KSI in tension. How do we feel about that? Feeling okay? All right. No questions. Let's look at the transverse shear then. Sorry, the shear stress. Okay. So we could have some contributions from torsion, and we could have some contributions from transverse shear. All right, let's go back up and look at our picture. And first thing I probably want to do is look at my torsional term. So in general, I know that torsion is going to be something like TR on J. So let's take a look at what's going on. Do I have a torque in this problem? Well, yes, I have everything in this problem. So here's my torque. It's this 600 inch-pounds sort of into the negative y face. It's kind of trying to turn it in this general direction. So what that means is that 600 inch-pounds is kind of trying to sort of rotate this guy this general direction. When I get off the bus, kind of on the perimeter at point B from the 600 inch-pounds, I'm only going to be pointing down, which here is the negative z direction, but we're on the negative y face. Hi there. Say hi. That's my wife. Okay, so if we have negative y face, negative z direction, that means we're going to have a positive tau yz here. Everyone cool with that? Any questions on that? All right. All right. And then what about my transverse shear? Well, that's going to look something like VQ over IT. And let's investigate maybe what subscripts we should be putting on here for that. So we're, again, investigating point B. just here. And so I want to think about, all right, yeah, I've got some loads coming across the face. I've got the 125 load that could give me transverse shear, and I've got this 200 load across the face that could give me some transverse shear. So which one of these is going to be influential if I'm investigating point B? Well, I think about, all right, let's draw my variable T, which is the thickness of the piece across the piece at the point of interest. If I'm thinking about the 125 load, all right, it's going sort of this direction, you know, left and right. So drawing a line perpendicular to that at B is going to be my nothing line, okay? So this 125 not contributing anything at B because I have this nothing line that makes my Q equal to 0. All right, so I'm not going to really have to concern myself with the 125. All I really do need to concern myself with is the 200. I do have this guy that I need to concern myself with. Right? So I draw a line across my piece at my point of interest, and that's going to look like this. This is my variable T now. That's T, the thickness of the piece at the point of interest, giving me all this for what would be my A prime term. Similarly, if I'm going to continue on, I need to sort of calculate what the centroid is here of this particular guy. This here is my y bar prime. Which, if we remember our equations, is 4r on 3 pi for a half circle. And it's on your equation sheet if you don't remember and you need it tomorrow. Maybe you will. Okay, so let's put that all together and remind ourselves that we're concerning ourselves with this 200 pounds. So this is on the negative y face, and this is in the negative z direction. So this is also going to be giving me a positive tau y z. So both of these terms are positive tau y z's. Good times, good times. Yeah, this problem is just like the most complicated like coordinate system and everything you could possibly imagine. All right, so the torque value, we know it's 600 inch-pounds. The radial coordinates, just the radius of the piece out to point B, which is 0.5 inches. J, my polar moment of inertia, this is pi on 2, r to the 4th. Bang. Plus V, this is my shear load coming across the face. It's this 200 pounds here. Hopefully I can fit in my Q, which is A prime y bar prime. So the area here is going to be pi on 2. We have half the area, radius to the 4th, 0.75. Sorry, not to the 4th squared. It's over just a touch. And then y bar prime, we said is 4r on 3 pi. So this is 4r, 0.75 inches on 3 pi. Good times. Alternatively, you could maybe, if you want to try to remember, that this whole thing together looks something like 2/3 r cubed. Maybe you can see that. But you don't necessarily have to remember that. If you can just remember y bar prime, A prime, you don't even have to remember that either. That's on your equation sheet. All over IT. So IT is pi on 4, radius to the 4th. And the thickness is just 2 times. Wait, why am I doing 0.75? The radius is 1/2. Gosh. Oh, sorry, guys. That's why pencils have erasers. Okay, sorry, it's all 1/2 inch radius. times the thickness here, which is 2 times 0.5, which is 1 inch. All right, all this added together, just cut to the chase. This is 3060 psi plus transverse shear contribution is 340 psi. So we see torsion kind of contributing significantly more here than the transverse shear. But all in all, at B, we have this zy or yz. They're both the same. It's going to be 3.4 psi. What a doozy. That problem is a doozy. That coordinate system really just kind of shakes it all up, huh?
Could you explain why the torsion and the transverse shear stress are positive again?
Sure. Go back to my beautiful picture that's now all messed up. Oh, look at that erasing. Mad skills. All right. So this 600 inch-pound torque is what is concerning us, right? So let's talk about the torque first then. Stick your thumb into the board, right, or into the page, and then twist. That is going to give you a twist that looks like this, right? It's giving you this counter or this clockwise twist. You okay with that, Andrew?
Yes.
And I know we had questions about right-hand rule with moments, but the torque seems
Yeah,
to be
I think I
okay.
got that down now, though.
The torque's good?
Yes.
Okay. So the idea then is that, all right, I'm rotating in this clockwise fashion, and I'm going to get off the bus at point B. I'm getting off this circular torsion bus at point B. And when I do that, I sort of point in the direction where I would be continuing my motion, more or less. Okay? Is that clear?
Yes.
Okay.
Oh, is it because it's negative z and negative y, and that's
Yeah.
what makes it? Okay, I forgot we were on the negative y face again.
So this is the negative y face, negative z direction. Got it?
Yes.
That gives me
I don't
positive.
like this coordinate system.
Yeah, not the best. I'll give you that. Not the easiest to work with. And then the transverse shear, it's a similar idea. This guy here is coming in the negative z direction, but we're on the negative y face. So positive tau yz.
Okay, thank you.
How are you feeling on that? That one's a doozy. If you're at least somewhat comfortable with that one, or at least understand where I'm coming from on that, in most of the case, you're probably good to go. I promise the combined loading problem tomorrow is not that hard.
Quick question. If we were looking at point A instead of point B,
Mhm.
The 1600 moments, that would put A into the top of the rod in detention, right?
Yes.
Okay, cool. Just wanted to make sure.
Yep. And I mean, you could visualize that too, even maybe in the problem, just by looking at it again. Is that all right? That 1600 inch-pound moment is coming from this 200 pound force. Okay, that's wanting to sort of like pull this entire thing downwards, putting tension at A and compression on the bottom. You got that, Yusuf?
Yeah, I find it a little bit harder to visualize it using the forces on the diagram. And I kind of understand the right-hand rule now. What I was doing earlier is I was just curling my fingers, and then in the direction that I was curling my fingers, I thought that was the side of compression. But you have to go around until you hit the point, and then where the point moves is. I got you now.
Okay. Yeah, I think
That's exactly what I was doing too, that I was doing wrong.
Yeah. I just figured it out now.
Yeah, okay. Yeah, the double arrow for bending is always a tricky one. I think about it like being fixed into the wall, and how would I have to try to like curl it if I wanted to do right-hand rule with it? You know what I mean? That's kind of how I
If we
think
were
about
looking
it.
at the positive Y face, then and like B was on the left, then
Yeah.
it's always in the left side will always be in tension. That, I mean, most of our examples were like that. That's why I was confused.
Yep. Well, if we were looking at the other face, this arrow would be pointing upward. How about that for confusing you? Yeah, let's not go there. Okay, how are we doing with that?
Are there any other questions on the exam review that you feel we should be prepared for or with?
all of them.
No, but if you had to like single one out.
Now you're just fishing.
Yeah, well, I mean,
everything is game. I mean, all of these things, like this distortion stuff, where something that looks like this, we did a lot like this. This guy here, we have two different bars of different materials. How do you handle angle of twist? You got to be able to know that. Stress concentrations. I mean, you got to be able to know how to read this chart and understand the stress concentration. One thing that might be a little tricky is that this R here, this is the radius of the notch. And sometimes you'll see an equation, okay, let's just talk about this for a second. Because this can be a little tricky. Is it like, all right, let's say you got this equation here, or this figure here, and you have this radius. Well, this is the fillet radius. This is the notch radius. I was thinking about this while I was doing this problem. And that when you're calculating your shear stress, you're using the equation TR on J. But in this shear stress equation, the radius that you're using is actually the physical radius of the bar, which is a different R. So it's a little confusing to have this notch radius have the variable little r, but when you're calculating the shear stress in the bar, you're using what is this variable, which is like d on 2, as your r that gets plugged in here. Is that clear?
yes.
So just make sure you're clear on that. Yeah, that I realized that when I was kind of like doing the solutions for this one, I was like, yeah, that little r is a little annoying.
So real quick, can you scroll back up to the diagram?
Huh?
So on the bottom axis, when it says R over D, we're talking about the notch radius over little d, right?
This is based on this figure. So little r, this is the fillet radius.
Okay.
Little d here, this is the smaller diameter after the notch has been removed, like taken out of the material.
Okay.
Yeah, so in this portion of the rod here in the center, you want to calculate like, well, what's the shear stress here without the notch? It would be like TR on J, where in that case, R is D on 2. And then that gets amplified because of this notch according to this diagram. Let's just talk about it really quick because it's a little confusing. So I make a cut here in this cross section. I want to look on that guy. If I'm looking at that guy, this has what is little d as my diameter. So in that case, what I would normally draw is, all right, this is the radius, which is d on 2. So I'd want to calculate, well, what is tau without notch? Well, that looks something like the torque that I applied, d on 2, which is r, on j, which is pi on 2, in this radius, d on 2 to the 4th. Hopefully that's clear. And then once
wouldn't we use the larger d then?
No, use a smaller d. So
Okay.
in the center of this bar, I'm calculating, well, what's the shear stress here in the smaller portion of the bar? And then you amplify from there, right?
Okay.
Based on this chart. Okay. So this would be like what it would be without notch. Okay. But with the notch, you get some amplification. Let's call it tau K from amplification. It's the stress concentration factor times that shear stress that you calculated if the notch didn't exist. Understand?
Yeah.
Okay. Bending. You got to know your like shear and bending diagrams. So let's take this as an example. I mean, this is a very simple example. Here I've got two kids kind of on a teeter-totter. They each weigh, what does it say, 90 pounds? All right, well, you got to know your shear and bending diagrams. And this goes back to statics. What is the shear? At the moment. Well, you know, the free body diagram is going to look something like this. There we've got this 90. Yeah, this is going to be 180 to balance everything out. Okay. So your bending diagram or your shear diagram is just going to look like this. And then your bending moment diagram will look like this in this case. Got it?
Professor,
Kyle.
can you run through the bending diagram really quick? I still forget how to do it.
Okay. So full example here for bending diagram. Let's take this problem for example. So we kind of already have the free body diagram. You know how I got the free body diagram? Yes, this isn't a problem?
I do understand. I
Okay.
understand.
Okay. So you can see that this beam then is kind of broken up into two sections, right? Let's call it region 1 and region 2. Understand that? I want to investigate what's happening in region 1 of the beam. And if I do that, I want to make a free body diagram of a cut at some random location in region 1. With me so far?
Yeah, I'm with you.
Okay, so I make a cut at a random location that's at a position of X. Following? Inside, I have this 90 pounds, right? And then in order for this thing to be in equilibrium, I need to balance that out with an internal shear force and also an internal bending moment. Anywhere that you have one object fixed into another, you have reactions between those 2 points. So in this case, we have like this side of the bar fixed into this side of the bar, okay? And so inside of that beam, we have these reaction forces and moments that keep everything together. And that's what you're looking at here. And in order for equilibrium to hold, we must have some of the forces equal 0 and some of the moments equal 0. Okay, so let's do that. If we want some of the forces equal 0, we're going to have negative 90 pounds plus our Vx equals 0. So what that means is in this portion of the bar, the shear must be 90 pounds. Is that clear? Regardless where we cut in that region, region number 1, the shear must be a constant value of 90 pounds in that region. Have I lost you in that train of thought, or are you cool with that?
I'm with that. I'm with you.
Okay, so that's why you see this constant value of 90 pounds drawn in that first region of the beam in my shear diagram. Okay. Now let's look at the moments in this portion. So if we want the moments equal to 0, well, we have this moment that is our moment of interest that exists. And then if I'm standing at this location, let's call this point O, and I'm taking my moments about point O, then the only other thing that's going to contribute to that moment is this 90 pounds. And that 90 pounds is the distance of X away from my current cross section. Okay. So the moment from this 90-pound force is something like 90 times x in a positive fashion. So plus 90x. The farther away I get from that left-hand side, the larger the moment becomes. Following me on this?
Yes.
Okay, this all equals 0. So in the end, you're going to have something like mx is equal to negative 90x. This is solving for my moment x. This is negative 90x. So I've actually reversed my diagram here. My diagram should point down. Sorry for that. Something that looks like that. Here, this is my equation, mx equals negative 90x. Understand that? This is the equation, m is negative 90x. The downward linear line with its origin at 0. All right, so when x is 0, my moment is 0. And at the end of this region, which happens to be 8 feet, my moment is maximized, which is negative 90 times 8, which is negative 720 inch-pounds. How you doing on that?
That makes sense, yeah.
Okay.
Professor,
that's all
based on your shear force diagram, can't you use the shear force as the slope of
Yeah.
the moment? So wouldn't
Yeah.
it be 90x? Like positive, like the way that you had it?
Yeah, so by convention, typically you would draw this shear downwards.
Yeah.
And in that case, you could do that. So if you draw shear downwards, which is sort of the conventional way, your diagram flips.
Yep.
We're going to confuse Kyle now.
Sorry.
So this would be negative 90, negative 90. And that is the slope of this region, negative 90x. So these guys are related by a derivative, right? So it's dm dx is equal to negative, sorry, positive v. Hopefully that's clear. Maybe you talked about that in statics, maybe you didn't. We are going to talk about that a lot next week. So if it's not clear now, it will be clear next week.
Thank you.
Better? You could repeat that process for this portion of the beam as well. Make yourself a free body diagram of a cut that's random in region number 2. Sum the forces, sum the moments, figure out what the equation of the shear and the equation of the moment are in those regions. So for some, simple cases, you should be pretty comfortable, right? So you got, we've talked about 4-point bend quite a bit in this class. If you have a symmetrical 4-point bend situation, you're going to have shear and moments that look like this and this. So this is a common shear and bending diagram for a 4-point bend situation. You might have a cantilever. This is a common situation as well. Your shear is consistent in the cross section. It's a constant value. And your moment is maximum at the fixed end and goes to 0 at the far end. All right, these are just common examples. 3-point bend. We just kind of saw. We just have the inversion of that, since our seesaw is like upside down, kind of by comparison to this. How are we feeling with that?
Feeling better.
Kyle's feeling better. That's good. Okay, kind of approaching an hour here. Any other specific questions about the homework problem or sorry, not the homework problems, but the practice problems? It's just typical bending moment calculations. Oh, but we do
I
have
had a
factor of safety. Go ahead, Kyle.
I had a question. It's on the one below that, number 6.
Mhm.
In your solution, when you were solving for the area moment of inertia, you didn't include the base, you just included the height. And I was wondering why you did that.
Let me look at the solution here. It's number 6. Oh, okay. Right. Let's look at this guy. All right. So Kyle wants area moment of inertia of this box beam. All right. So just for reference sake, we understand that the inside here is 3 inches. So it would be this 4 inches minus 2 times 1/2. You okay with that? And then this dimension is also 3 inches. Again, it's just 4 inches minus 1/2 and 1/2. Green light on that, Kyle?
Yes.
Okay. So typically, you would have something like I for the outer box minus I for the inner box because they share the same central point. You understand? Or if I sort of call this my inner box and I call this my outer box. Following that logic?
Yep.
Okay. So in that case, I have what is 1/12 BH cubed minus 1/12 BH cubed. You agree?
Yeah.
Where we have like the outer and the inner values for the base and the height. So outer and inner. Okay, well, what are the base and the height for the outer? Well, 4 and 4, right?
Mm-hmm.
What's the base and the height for the inner? 3 and
I see
3.
what you mean now. I see what you mean. I
So
see.
here we have 1/12, 4 inches to the 4th
It's to the 4th. Okay.
minus 3 inches to the 4th. Capiche?
Yep.
Yeah, that tricky 4th in the solution.
I also have a quick question on number 6.
Uh-huh.
For the thickness, you used 1 inch. Is that because there's a 1/2 inch on either side?
Correct.
Okay.
So you're interested in the max shear at A. That's basically what you're calculating for this problem. So when it comes to that, you'll need to find what is Q, which is A prime, Y bar prime, right? So at point A, you're kind of like right at this portion of the box beam, right?
Yeah.
And we sort of saw this with I-beams as well, where when you go from like a skinny part to a fat part, we know that we have much more shear in the skinny part. Right, so when you're like right on this boundary between the skinny part and the fat part, you kind of go with the lower value because we have this smaller thickness that needs to bear the brunt of all the stress, right? So instead of picking like what is the full width of this box beam, we're going to look at this little slice. But you got to be careful because the full width of the piece at A with that little slice is not just this little slice. You've got to go across the full width of the beam, which is 2 1/2 inch segments. So the total thickness for this portion of the box beam is 2 times 1/2 inch, which is 1 inch. Clear?
Yeah. I just wanted to make sure.
Yeah, I kind of wrote it that way in the solution just so it was a little clear, more clear.
Okay. Thank you.
The A prime calculation for Q at A would be 1/2 by 4, right?
Yeah, so if you want to do A prime here, you're looking at this area above this guy.
Okay.
That's 4 by 1/2. And then if you want Y bar prime, which is kind of up to here, that's
Composite body.
1.5 plus. Well, we know that the centroid of this particular piece is just 1/4 of the way up, right?
Yep.
So it's 1/2 of 1/2. And then you know that this inner box is 3 inches. So this distance to the bottom of that top portion is 1/2 inch. So your Y bar prime is 0.15 plus 0.25, 1.75. Is that, you following that?
So you could just add them.
Yeah, in this case. I mean, you know that this guy has its centroid. So this is the area that you're interested in, right? You know the centroid of this area is the centroid of a rectangle, which is just half the height,
Mhm.
1/4 inch, right? So if you want to get there then from this, you've got to travel all the way up, get to that point, and there you are. It's much more difficult if you had to do the analysis in the center. Like, let's say you were interested in the shear stress at this location. Let's call it like little b or something. Well, now I got to make my line across the bar this way. And now my A prime is all of this. So I've got like a composite body with 3 rectangles, and it's much less clear what the Y bar prime is of that particular cross section.
Yeah.
It's probably somewhere like here, which is a bit annoying to calculate. You'd actually have to do the composite body calculation for this.
Thanks.
Isn't this fun? Yes. Math, beams, forces.
Thank you, Professor.
Who wants to be Spider-Man when you could be Mechanician Man?
Have a good night.
Any other questions on the homework? I keep calling it homework. It wasn't homework.
I
That was
think that's
Ivy.
all my questions. Everything else felt pretty good.
All right. You guys are going to dominate tomorrow. I'm excited.
Hope so.
Thank you, Professor.
Yep, you're welcome. Good chatting with you guys. We'll see you tomorrow. Get good sleep.
All right. Thanks, Professor. Have a good
Have
night.
a good one. Thank you.
Okay. Bye, guys.